Thanks a lot, Daniel. Thank you very much, organizers, for giving me an opportunity to give this overview talk on the positive geometry of scattering amplitude. So this is a very broad subject now. I'll try to do a particular path through that subject, giving some introduction for people who have never heard about it, what the positive geometry is, and give some examples where we apply it in the case of scattering amplitudes. So just to define what we will be talking about, so the scattering amplitude for me in this talk will be a rational function of kinematics. So it will be either a tree-level amplitude or the integrand of loop amplitudes. So most of the time, except for one one small discussion, we will not talk about the final amplitudes. We will not talk about polylogarithms or any other functions. We will talk about rational functions, tree-level amplitudes or loop integrands. So the functions which you would obtain from collecting Feynman diagrams prior to integration. And we know that there are many different ways how to calculate scattering amplitudes, different ways how to expand it, standard method of Feynman diagrams. There are different recursion relations, off-shell, on-shell. We have CHY formula. We have many different methods how to get, in a given quantum field theory, scattering amplitude using modern methods. Now, the motivation which leads us eventually to positive geometry, or the application of positive geometry in the context of amplitudes, starts from the idea that we would like to define the amplitude as a one object, not using an expansion, not as a sum of pieces, but as a one object. And find some intrinsic definition to what is the scattering amplitude. Now, this is a very old idea. It goes back to the analytic S-matrix program, when back in 60s, before the discovery of QCD, people tried to define and calculate the scattering amplitudes as a unique object which satisfies certain constraints, is uniquely specified by these constraints. This was unsuccessful back then because also the question was extremely hard. They asked the question about some pion scattering to non-perturbative, to all loop orders, which was extremely hard, and they couldn't find enough constraints to uniquely specify these amplitudes back then. But this idea actually comes back in recent 1-2 decades in many different implementations. One is, for example, symbol bootstrap, revival of this idea in the perturbation theory, when the loop amplitudes or the essential information of the loop amplitudes given by symbol are also uniquely specified by certain conditions. Now, we will ask here, and this will lead us to positive geometry, a simpler problem. We will ask the question about the rational function, about these tree-level amplitudes and integrands in perturbation theory. These will be rational functions of kinematics. They will have poles, singularities, and they have to satisfy some physical conditions, what they do on these poles or singularities. They have to factorize, there are soft limits, collinear limits, and other conditions. Now, if we have enough constraints for some amplitude in a given quantum field theory, and we know that these constraints uniquely specifies this amplitude, then we can turn it around and use it in some recursion formula, for example. So the BCFW recursion relations are exactly based on these conditions that only factorizations, only knowing where the poles are, and the amplitude factorizes on these poles, is enough to reconstruct the amplitude uniquely. So from this point of view, the amplitude is an answer to a question, what is the unique object which satisfies certain constraints, such as factorization or different kinematical limits. Now, we would like to go farther and give a more direct definition of the amplitude, at least in some very limited setup, which I will give the examples later. Not as a solution to some list of constraints, but directly saying the amplitude is something, and in our case, we will say that the amplitude is a volume of some geometric space. This will be the connection to positive geometry. The positive geometry will give us some geometric space, and for certain cases, the amplitude is a volume or some differential form on this geometry, and that reproduces the scattering amplitudes. So this is a direct definition of what the amplitude is. Now, in general, there are two parts of this story. The first part is a combinatorial math. So once we have this list of conditions that the amplitude satisfies, such factorizations, positions of singularities and properties, what happens on these singularities, we will map it to boundaries of the geometry. So a singularity of the amplitude will correspond to a boundary, some boundary of the so far putative geometry, which will capture the amplitude. And the second part is to calculate the amplitude and how to get from the geometry the amplitude itself, and this will be done through some volume form, volume or canonical differential form. Yeah, we'll say more in details what this object is. So this is the motivation. So we start with an amplitude which is uniquely specified by certain conditions. The logic is to map it to some geometry and then calculate the amplitude as a function from this geometry. Now, in practice, once you already defined the geometry for the amplitude, in order to calculate the amplitude itself, this volume, the best way or the most practical way is to triangulate a more complicated geometry into smaller pieces. Like here, let's say the amplitude corresponds to some polyhedron, and to calculate the volume of this polyhedron or this differential form on the polyhedron, it's simplest to triangulate it into elementary building blocks, which are tetrahedra in this case. And then the volume of each tetrahedron is simple function, and then we have to just sum over it. So, and this works in general. So once this relation between the geometry and amplitude is established, different ways how to calculate amplitude, even these standard physical ways using recursion relations or Feynman diagrams, correspond to different triangulations of the geometry into elementary pieces. And here we will discuss the two prime examples that we have. We don't have a general map between theories and amplitudes and geometry. This is a much more complicated question, so we have to kind of go one by one, figure out if there exists a geometry for a given theory. And the two examples that we have are kind of on the opposite spectra of your theory space. So one is phi cube theory, a simple scalar theory, either with two pairs of colors by a joint phi cube or trace phi cube. This is realized by so-called ABHY associahedron. So there is some geometry called associahedron. This actually has been known in math literature for a very long time. And then it was discovered that there is a connection between this geometry and phi cube amplitudes. And the other example, which predates the associahedron, that actually came first, is the amplituhedron, which is the positive geometry for planar n equals 4 super-Yang-Mills theory. So this is the simplest QFT from many point of views. It has a lot of symmetries. It has maximal supersymmetry. It's conformal symmetry, hidden symmetries, dual conformal symmetry, Yangian. And, but it is a very complicated theory if you just look at the particle content. And, but as we know from long 2-3 decades of the work on this theory, the amplitudes are surprisingly simple and exhibit a lot of properties. And, therefore, it's not completely surprising that this is exactly the theory where the positive geometry plays an important role and the amplitude is captured by the amplituhedron. So as I said, at the moment, we don't have a dictionary between a theory and a geometry. So we have to kind of go one by one. There are two things which at the moment are challenges to extend the space of quantum field theories we can talk about. And the first one is non-planarity, or the lack of color or flavor ordering of the amplitude. Because for both of these theories, we can always expand the amplitude in terms of some ordered amplitudes when the particles are ordered on a disk, so there is a given ordering. And this is very important because the amplitude is then sum of planar diagrams we can use planar global variables, and we can really talk about the loop integrand as one object as a sum of all contributions, which has some unique labels. While if you lose planarity, there is always a problem with labels, what type of labels you use, and what does it even mean to talk about the integrand. And the other challenge is this map between singularities and geometry, because this worked extremely well for IR poles. By IR poles, I mean poles at small momenta when some p square is 0, where p is a momentum flow in a diagram, or p square from the propagator. But in general, the amplitudes also have poles at large momenta, referred to as UV poles. And while the unitarity controls what happens for these IR poles, the amplitude should factorize, or for the loop integrands, there are cuts when you cut the loop amplitude into a product of 3-level amplitudes. For these UV poles, we don't know what the general physics principle tell us. What happens with the amplitude when you send some momentum to infinity, either the loop momentum or the external momentum. So we don't know how to map these singularities to geometry at the moment, because we don't know what the amplitudes a priori does on these poles. Now, there are, of course, work on all of these questions. There is some intriguing connections between these, the trace by cube theory, to other theories which do have poles at infinity, which is, for example, the nonlinear sigma model, or even the non-supersymmetric Yang-Mills theory. And there have been a lot of progress this year on understanding these theories by Nima Khan-Hamed and Song He, and students, Carolina and Dong. And yeah, they published a series of many papers that address these connections between trace phi cube and these other theories. So hopefully there is also some something more to learn about how to this link between these poles and infinity, and even non-planar pieces, and how to see them in the geometry. Okay, so this was kind of a longer motivation. So let me now start from talking about the positive geometry, what it is, and what are these 2 prime examples, how to extract the amplitude from the positive geometry. So, so there is some mathematical definition of what is positive geometry, but for us, we can use very pedestrian way how to talk about it, is some d-dimensional space which is given by polynomial inequalities. So we will start from some kinematical variables like the momenta polarization vectors, and we map them to some parameters. There will be either some xij parameters or momentum twisters and so on, but it doesn't matter. In general, there are some parameters xi which parameterize our kinematics. And there will be some polynomials in these parameters, and we are just given inequalities. So all of these polynomials, let's say, must be positive. So they carve some space, like here. Yeah. So this is some curved space which is carved by 4 different inequalities. Yeah. Saying that this polynomial is positive or non-negative means that we have to be on the right side of that boundary. When the polynomial is 0, this is a boundary of the space. Okay, I will give a number of examples later to make it more concrete. And the second thing, that the positive geometry is equipped with a canonical differential form omega, which has logarithmic singularities on the boundaries. So we start with some differential form, d-dimensional, and whenever we approach a boundary, when one of the parameters, let's say, is 0, so let's say x is 0 is the boundary of the geometry, then the form gives us dx over x times a form which is a differential form on the lower dimensional boundaries. So in this case, we have a positive geometry here. So if we go on one of these boundaries, for example, this line, we would generate dx over x, where x is 0, approaches that line, times the differential form on that line. Okay, so what are the simple examples? So the simplest is one-dimensional example. This is a simplest example of positive geometry. X is positive, it's real. X is real and it's positive. So the positive geometry is just a semi-infinite line segment from 0 to infinity, and the canonical form is just dx over x. It has singularities on the boundaries. There are two boundaries, x is 0 and x is infinity. So dx over x has two poles at 0 and infinity. So this is the correct differential form for this positive geometry. And we will also, for the later notation, once we see dx over x, we call it d log x. In general, there will be some more complicated arguments of these d log forms. Next example, still one-dimensional, is a finite line segment. So x live between x1 and x2. So this is given by two inequalities, which are here. X is bigger than x1, and x is smaller than x2. And then the differential form, the canonical differential form on this line segment is given by this formula. So you see two poles in the denominator. There is a pole when we approach one of the boundaries or the second boundaries. And there is some numerator which just depends on x1 and x2. And it's there for the normalization of the form. So once you calculate the residue of the form on one of the boundaries, you should get 1 or minus 1. So you can also change the variables from x to other variable f, which is given by this ratio. And then the form has a manifest d-log structure, so it's then just df over f. So we will write it as d-log and then the argument f, which is equal to x minus x1, x minus x2. So this is what we would refer to as d-log form. We can write it like this. This is perfectly fine. But if we want to make manifest this property that near the boundary it behaves like dx over x, we have to change the variables to write it in this d-log form. Okay. Any questions about this simple example? Yes?
Want dx over x at the boundary.
That's the definition of the form. So you don't want dx over x squared, you would like dx over x. Now the moral why we want that is that it is projective. So if you rescale x, then this form is invariant under it. Yeah. This is basically to capture how the singularities of the amplitude behave. But if you are just in the mathematical world, you don't care about amplitudes. It's that this is a natural form which is invariant under projective scaling of the x. Okay, thank you. So let's do a two-dimensional example. So the simple example is a positive quadrant. So x and y run from 0 to infinity. X and y are positive. And the d-log form is so this is the positive geometry. And the d-log form is very simple. It's just dx over x and dy over y. Now the more interesting example is a triangle. So now it's bounded by three boundaries. So x is positive, y is positive. So the boundaries are x is 0, y is 0. And then we have also this boundary. Y is equal to 1 minus x. To be on the right side of the boundary, y must be smaller than 1 minus x to be inside the positive geometry. So these are the ranges for x and y, if you just look at these inequalities. And you can write a form. It has three boundaries, x, y, and 1 minus x minus y, which corresponds to this boundary. And this is the correct form. It's already correctly normalized, as we can, for example, check from taking a residue on one of the boundaries. So if we are going on a boundary when y is 0, it's this boundary, then this form needs to reduce to the form on the line segment that we already calculated before. And this is a line segment from 0 to 1, and this is a correct canonical form for that. Okay, so this is already a first slightly non-trivial two-dimensional example, triangle. And we will talk about triangle a lot later. Now, let's do a slightly more complicated geometry, which is a polygon. So we are still in the plane. It's a two-dimensional space, but now we have four boundaries. So the four inequalities which define the geometry are given here. The inequalities become equalities once we approach the boundary. It has four boundaries. And so the differential form must encode that in the poles. So there are 4 poles over here. And now there is some numerator as well. And if you just want to write a form, we have to fix the numerator. Just knowing what the poles are still completely doesn't fix it. The differential form has some interesting numerator. Now there are 2 ways how to fix, to actually calculate a form. One is triangulation, because we already solved the problem for the triangle. So we can divide the quadrilateral in the set of 2 triangles by adding this line, y equals 2x, which connects these 2 vertices, and divides the space into 2 triangles. And then for each triangle, we can find the differential, this D-log form in a simple way. It's very analogous to what we did before for the triangle. And then the form for the whole quadrilateral is a sum of these 2 forms. Now note that each of the form has this pole y equals 2x, but this is a spurious boundary. Yeah, it's there in the triangulation, it's used by the triangulation, but it is not there in the final result. And indeed, once you sum these 2 forms, this pole cancels and you get only 4 poles and you get a numerator here. Now, what is the role of the numerator? That can be seen from a different way, how to calculate a form. It's there to cancel some spurious singularity. So if you just look at the denominator of this form, it has correct singularities at these 4 boundaries. But if you set 2, it's a 2-dimensional space. So you can go on a second boundary, which is a vertex. And the form generates a singularity at these 4 vertices corresponding to adjacent pairs of these lines, but also generates a singularity over here, which is an intersection of this boundary and this boundary. This is y equals 0 and y equals 1 plus x. So if you send to 0 this y and this bracket, you would generate a singularity. But this is a spurious boundary, because this is not a vertex of our positive geometry, it's outside. So the numerator must cancel it, and you can actually use it as a condition to fix the numerator. Now, in the previous way, if we did the triangulation, it came automatically in the numerator. So you see that the numerator has a 0 when x is minus 1, which is exactly the location of this spurious point over here. And we can indeed check, consistency check. If you start with the form and you go on the boundary y is 0, you would naively get 3 poles, x, 1 minus x, that's the correct one, but also x plus 1, which would correspond to this point, so the numerator must cancel it, and indeed it does. Yeah. So we again in the end just get a form on a line segment, which is this line segment. Okay? Any questions about that? So the 2 ways how to calculate these forms, the most standard way is to do the triangulation, but sometimes we can also use the requirement that the form doesn't generate singularities at unphysical locations or spurious locations to fix the numerator of the form. Okay. Now, so this will work, this logic works now for, let's say, general polygon. But now we would like to rethink the triangle again. So far we spoke about the triangle in a plane. It's a positive geometry. It has some interesting canonical form. Now let's start with the triangle again here. Has 3 vertices, z1, z2, and z3. These are the coordinates of the vertices. And we consider some point y somewhere in the triangle. So it has coordinates x and y. And now we embed, so these are 2 vectors, all of these guys are 2 vectors. We can embed it in the 3-dimensional space by just adding coordinate 1 in the first slot and leaving 2 and 3, second and third slot as the coordinates of these 2 vectors that we have here. So now these are 3-dimensional vectors, and we can actually take these 3-dimensional vectors and calculate 3 by 3 determinants of these vectors. So we define a bracket y1, 2 to be determinant of vectors y, Z1 and Z2. So it's a 3 by 3 determinant, and we get some results. This is Y, this is another determinant, gives us X, 1 minus X minus Y, and 1 for the determinant of just Z1, Z2, and Z3. And then there is also some measure that we can write in this form. Now, what is the logic of these determinants? So this now bracket or determinant will be 0 when Y is a linear combination of 1 and 2. So once we take point Y and move it on this line 1 and 2, this would be 0 because now they are proportional. And this indeed corresponds to Y equals 0. Yeah? So this makes complete sense. So we are basically doing what we did before, but now we enlarged these coordinates here in this three-dimensional space and define these brackets as exactly give us these three boundaries that we had here. So this allows us now to rewrite the differential form, which was the differential form for the triangle, in this way. Yeah? When these are the determinants of these vectors here. And indeed, if you take now the coordinates for Y, Z1, Z2, Z3, plug back here, you again get the form that we started with. Now, why this is interesting or useful is because this form is actually projective in all variables. So if we rescale Z1, Z2, Z3, or Y, this form is projective. So this is not only form for this kind of artificially embedded coordinates in three-dimensional space, but it's actually a form on the triangle in the projective space. So you can now think about these coordinates as projective coordinates, and this is a projective plane, not just a real plane, but projective plane. We will get back to it later when we talk about the amplituhedron, because that will be the main ingredient, because these variables will be actually momentum twisters, not just some arbitrary variables, and they will capture the kinematics of the gluon scattering. But before going to amplituhedron, we now discuss the simpler positive geometry, which lives in a more natural space, which is associahedron, which captures the three-level amplitudes for trace phi cube theory. Okay, so what is the theory we are talking about? It's by adjoint scalar theory. We can define it by Lagrangian with some kinetic term and some cubic interaction term. The amplitude can be organized using two different orderings because there are two different group structures here. So we can do two different trace strippings of the amplitude, and there are two orderings. For our case, we actually focus on the situation when the both orderings are the same. So we actually get only one ordering. So this is a trace phi cube theory. Despite there is a generalization of whatever I say here to the full double ordered theory. Now at 4 point, the amplitude in this theory is very simple. It's a sum of these two Feynman diagrams. It's just phi cube, so the Feynman rules for vertices, they are just 1. So the result is just 1 over S plus 1 over T. Now we would like to interpret this amplitude as a differential form. Now, well, the natural way how to interpret it as a differential form is just write ds over S minus dt over T. There is a reason why there is a minus sign that will become obvious just in a second. But this is a way how to start from a function and write it as a form. Now, the thing is that there are two variables here, but we would like to interpret it as a form on the one-dimensional space. The S and T variables are not independent. The S plus T is equal to minus U. And we will treat here in this construction U as some fixed variable, as let's say number. It's standardly the minus U is called C, and we demand that it will be positive. So then the positive geometry corresponds to just a line, S plus T equals C, where C is, for example, 2 or 3. That's just a fixed number. And the positive geometry is this line. Now the S and T are related. S plus T is equal to constant. So also the differentials are related. So we can actually rewrite it as a one form. Yeah? We started with these two forms. which was suggested by the kinematics, and we rewrite it as a one form. And it's ds 1 over s plus 1 over t ds. Yeah. So, and the 4-point amplitude is just coefficients of this differential ds. Now, let's see how it works for higher point case. For that, we have to define planar kinematical variables xij. These are actually very familiar variables. It's just a sum of ordered momenta from pi up to pj minus 1. So you just sum pi plus 1, pi plus 2, dot, 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 up to pj minus 1, and you denote that you square, and you denote these variables as xij. Now, for x1 free, this is just p1 plus p2 squared. This is s for 4-point scattering. For x2 4, this is p2 plus p3 squared. This is t, again, for 4-point scattering. So in these variables, the 4-point amplitude comes from the differential form, which is just dx1 free over x1 free minus dx2 4 over x2 4, which you can write as a difference of two d-log forms. Now, the general tree-level amplitude you can obtain from a sum of Feynman diagrams. So you can calculate this form that you would like to interpret as an amplitude as a sum of all planar diagrams, when each diagram, based on the logic which was here, is just given by the product of all d-log forms corresponding to all propagators. Yeah? So you just take the arbitrary cubic diagram in this phi cube theory. You just take d-log for all of the xij's corresponding to propagators. And this would reproduce the form for the endpoint amplitude. But this is a little bit backwards logic, because we haven't defined what is the positive geometry. We would like to, this is just rewriting the amplitude as a differential form. Now we would like to get the same result as the differential form on some positive geometry. And we already saw that the geometry must be lower dimensional, that is the number of variables in the game. In these 4-point examples, we had s and t variables, or this x1 free, x2 4, but the geometry must be just one-dimensional, not two-dimensional. Therefore, there are too many of these xij variables. They are all independent variables, but the geometry is actually lower dimensional. In fact, the kinematic space, the number of these variables is n times n minus 3 over 2, but the geometry that we are looking for is only n minus 3 dimensional. And this n minus 3 dimensional geometry is exactly given by this associahedron. So what is associahedron? For the simplest case, this was a line segment. It's this one-dimensional geometry. For the next case, for 5-point, it's a pentagon. And there are several ways how to define what the associahedron geometry is. One definition is that it's all possible triangulations of a pentagon, for this case. So each vertex corresponds to one way how to triangulate a pentagon, and each edge corresponds to removing one of the edge from the triangulation. And the two vertices which are adjacent to an edge exactly share that given edge in the triangulation. You can also think about it in terms of Feynman diagrams. Each vertex corresponds to one of the cubic Feynman diagram, and each edge corresponds to the same diagram when you compress two of the cubic vertices into a 4-point vertex, and kind of the bulk of the geometry corresponds to a complete contact term when you have one 5-point vertex. So this is the geometry. There are 5 Feynman diagrams. They correspond to 5 vertices in this geometry. Now, this is just combinatorically how to capture all the singularities. Now, in order to actually get the amplitude from this geometry, we have to do certain refinement of this associahedron, or a different version called kinematic associahedron. When we get the same geometry by working with these xij's. So we say that all the xij's are positive. These are our kinematical variables. And in addition, we have to also specify certain other conditions. So all sij's, which sij is pi plus pj squared, with minus sign, We call themCijs, and they must be positive as well. And there is a relation between these variables and these Xij variables. Yeah, this is just relations between kinematical invariants. And now we parameterize the geometry using n-3 of these variables Xij. There are many more of these Xijs. Yeah, as I said, there is this number of them, all n choose 2 minus the adjacent, which are 0 for the labels. So for the 5-point example, we can choose 2 of them, let's say x1 and x13 and x14 as parameters. And from this definition, this is the definition of the space, we rewrite these inequalities as inequalities on these x13 and x14 variables. This is like xy, when we did this example of triangle and quadrilateral. And now theseCijs are just numbers, they are just parameters. So we get 5 inequalities for x13 and x14. They are positive, but then they also satisfy some other linear conditions. And if you draw the space, if you look at the space, this is exactly the pentagon space. And that's the 5-point associahedron. So we have 5 inequalities, 5 boundaries. And x13 and x14 are kind of the axes in this space. Okay, so that's it. Yeah. So the 5-point phi cube amplitude corresponds to a differential form on the associahedron, which is given by this geometry. And now different ways how to triangulate. In the 5-point case, this pentagon corresponds to different ways how to write 5-point phi cube amplitude. And yeah, you can write it in many different ways. You can write it as a sum of Feynman diagrams, or you can do some completely different triangulations. Okay, so this generalizes to n-point. Yeah, this was our definition, but the 6-point example is already 3-dimensional, 7-point example is 4-dimensional, and so on. The associahedron grows the dimensionality with n. The dimensionality is n-3. Yeah. Now, there is some recent work by Nima, Arcani Hamed, Carolina Figueredo, and Francisco Basal, which is soon to be published, as we learned. When extends this story about the associahedron, this is a 6-point associahedron, so this would capture the 6-point phi cube amplitude, also to cosmological correlators and the wave function of the universe as one object. There was some recent work several years ago which interpreted certain pieces of cosmological correlators, diagram per diagram, as so-called cosmological polytopes. They were also positive geometries, but now they have a new story which captures the whole object, the whole wave function of the universe, as and also cosmological correlators as one object. And it's certain blow up of the associahedron geometry. You start from that, and then for each vertex you do some treatment to blow it up, to kind of capture that these cosmological correlators have more singularities than just usual singularities 1/p². They also correspond to energy singularities, and they are captured by these additional boundaries in the geometry. Okay, so that's the associahedron story. Any questions about that? So basically, it's about choosing the right variables, and then you define certain conditions, certain inequalities in these variables. You get some object, and the canonical form for this object, for this associahedron, gives the 3-level phi cube amplitude. Okay, there are no questions. I move to the polygons again. Now we ended with the triangle and the polygon. When we discussed the projective space, we said that the form that we wrote for the triangle made sense in the projective space. So these z coordinates were projective coordinates in the projective space. So we look at it again. We think about the triangle and the interior of the triangle in the projective plane. Now, point inside this triangle can be written as a linear combination of these 3 z's, the vertices. If you demand that all of these coefficients are positive, you span the interior of the triangle. Because we are in the projective space, you can always choose one of the coordinates to 1. Yeah. Kind of only the ratios between the c's actually make sense. Now, we can repeat the calculations from here. So because these c's are all positive, let's say C1 was 1, then the canonical form is just dC2 over C2, dC3 over C3, because the space, the positive geometry, corresponds to C2 and C3, running from 0 to infinity. And this is the right canonical form. And you can rewrite it in this projective way once you rewrite the c's in terms of these brackets that we discussed before. So this is a projective form for the triangle wrote before, but here can be written even from starting directly from the projective space, not just projectivizing the triangle in a plane. Now, we can extend it to talking about the polygons. So we define here 6, but n z's in a plane, and we can talk about a convex polygon and the interior of the convex polygon. Now there are some conditions. These z's can be random, because if you just draw random 6 points or n points, they will not form a convex polygon. So there is some condition of convexity, and this condition of convexity turns into some positivity conditions of a z matrix when you just enter the z's and you calculate minors of this matrix, and they must be positive. If all the 3 by 3 minors of this matrix are positive, then the configurations of points is convex. And formally, we can then write the interior of the polygon as a linear combination of these vertices with positive coefficients. And we can also write it in the matrix representation as C dot z, where c's are these coefficients. Here, we write it as a 1 by n matrix, and z's are elements of this 3 by n matrix of external data, these momentum twisters. And if we want to triangulate the space, or if we want to write the canonical form, we have to triangulate the space in terms of triangles and write the differential forms for each triangle individually, and then sum them up into the differential form for the whole polygon. And we have to write it in the projective form, because if we just use local variables for each triangle individually, you cannot sum them up, because each triangle would have different coordinates. You have to write it in this projective form to be able to sum it up as one object. Now, this is always a reminiscence of triangulation, that you get spurious poles in each individual term. So here we, for example, triangulate it like that. So each form separately has spurious poles, corresponds to these internal boundaries, which cancel once you sum everything together. Now, this is already very close to the amplituhedron. We are in some kind of toy example for the amplituhedron. But these, in some literal sense, these differential forms are amplitudes. In this case, some prototype for 3-level amplitudes. And there is a simple way how to go from the differential form to a superfunction. Basically, these y coordinates capture the supersymmetric Grassmann variables in a certain way. There is a very simple formula that you can start from, let's say, this form for the triangle and get some superfunction. This is not yet a super amplitude in n equals 4 super Young-Mills. This is for some simpler kinematics, but a simple generalization of that is already giving us NMHV 3-level amplitudes, and then there is a generalization for all k as well. Okay. Now, note that if we have this polygon, it has if you want to define it as a positive geometry, the polygons are very simple, or in general polyhedra, because they are only defined by their boundaries. So knowing where there are all boundaries already giving us exactly what is the geometry. Just being on the right side of each boundary defines the interior of them. Knowing the boundaries defines the geometry. This is not true in general for the amplituhedra, the spaces that we need for n equals 4 super Young-Mills theory. So let's quickly run into that. The amplituhedron is a generalization of the polygons. We discussed this simple case a lot, but the logic for the amplituhedron is very similar. It's a more complicated space, but the parameters are similar. The z coordinates just live in higher dimensions. They are not the projective variables in plane, but some higher dimensional projective variables. They are momentum twisters. They capture the kinematics of your scattering. And the simplest generalization is from polygons to polytopes. Polyhedra, polytopes, they capture some simple amplitudes like NMHV amplitude. And the general case is, is further generalizing this notion to Grassmannians. And then they capture all tree-level amplitudes and eventually also all integrands. Now, the Grassmannians are tricky because of one reason. In order to define the space, it's not enough just telling us, it's not enough just to tell what are the boundaries of the space. This was true for the polygon, but for Grassmannians, it's not true. You have to impose additional conditions, not just boundaries, to fully specify the space. We will see it in a simplest example of the Grassmannian G24. So this is a geometry of a line in a three-dimensional projective space. So line in 3 dimensions, moving line. It can be captured by 2x4 matrix, modulo GL2. It's a Grassmannian matrix, so 2x4 modulo GL2. You can choose your 2x2 2x2 minor to be, for example, identity matrix, if you explicitly parameterize it. And this space has 4 different boundaries. And that corresponds to sending some 2x2 minors of the C matrix to 0. In particular, minor 1, 2, 2, 3, 3, 4, and 1, 4. So, like the boundary of the triangle are just these 3 lines which define it. Here, the boundary of the Grassmannian is when minors of this matrix are 0. However, if you just do the similar as we did for the triangle or the polygon and just say that these minors have to be positive or bigger or equal to 0 to define the space, this is not enough. You have to also say something about the signs of other 2 minors, 1, 3, and 2, 4, which are not boundaries of the space. But we either have to say that they are both positive or both negative. So that's the first example when the geometry is not specified by boundaries. And the positive Grassmannian has these 2 minors positive. We have to specify these extra conditions, despite, again, they are not boundaries of the space. And the positive geometry, this positive Grassmannian, is just given by a statement that all of the minors, ij, all 2x2 ordered minors of this matrix are positive or non-negative. They are 0 on boundaries, except for these 1, 3, and 2, 4, which are not boundaries. And the D-log form is just given by 1 over 1, 2, 2, 3, 3, 4, and 1, 4, because these are the boundaries of the space. Now, the amplituhedron is a direct generalization of that. I will not give the full definition fits on one slide. It has several of these Grassmannian spaces which are kind of convoluted together, and you are just giving these, the analog of these inequalities for some bigger space. Yeah. But it has a definition which fits on the one slide, and that's the definition of the geometry. And the differential form on this geometry is a loop integrand in planar n equals 4 super-Yagnus theory to all loop orders, including the 3-level amplitudes. Now, I will here look at one particular case of that. So we will not discuss the general amplituhedron in more details, but we will look at the 4-point problem. So we will look at the simplest scattering in this theory, which is 2x2 scattering. So 4-point amplitudes. So we discussed this space G plus 2, 4 as the first non-trivial Grassmannian, first generalizations of polyhedra and polytopes beyond the case, which is where the positive geometry is fully specified by boundaries. We can think about it, as I said, as a line, as a configurations of all lines in the projective space. It's a 2x4 matrix. You can use parametrizations of the matrix. You can fix 2 of the columns to be 1, 0, and 0, 1, and leave undefined or unspecified parameters x, y, z, w in the rest. And then saying that all of these 2x2 minors are positive is telling us that that x, y, z, w in these parameterizations are positive. So this is a very simple 4-dimensional space. X, y, z, w are positive. It's an analog of a positive quadrant in a 4-dimensional space. So the differential form on this space is just dx over x, dy over y, dz over z, dw over w. And this turns out to be exactly the one-loop amplitude-hedron for 4-point MHV amplitude, loop integrand. We are just talking about loop integrants. And these 4 parameters, x, y, z, w, are basically 4 parameters which are in L, the off-shell loop momentum for one loop. So you can change the variables from this form to L back if you wish to, and you just get d4L over 4 propagators, and this is exactly a box integral. Okay? So in a very direct sense, these differential forms that we construct on these geometries are directly these objects in amplitude, the loop integrands. Now, so this was one loop. This was very easy. Now, thanks to this amplitude-hedron construction, we can now define the integrand to all loops. And the geometry is relatively simple. You just have L lines in this 3-dimensional projective space. Each of the lines has its own 2x4 matrix and own 4 parameters, which are all positive. If it was just this would be a very simple 4L dimensional space. This would be like one loop to the L. Yeah? But we now specify some mutual positivity conditions or negativity conditions between these parameters. So there are quadratic conditions between the different sets of parameters to different loops. So in the end, our positive geometry is given by 4L parameters, which are positive, and satisfies a number of quadratic inequalities. So this is a complicated space, but we can define it on 2 lines, what the space is. And the differential form on this space gives a 4-point integrand to all loop orders. Now, how do we find the form? We don't know. We would have to, the kind of direct calculational approach is just to triangulate this space. You have to resolve these inequalities. Yeah. But quadratic inequalities, like many quadratic inequalities, it's very complicated. But if you can resolve them, you can find some ranges for all of these 4L parameters. You can write differential forms. You just stack them together, and that's the result. Yeah? So the amplitude-hedron provides us a definition of the amplitude to all loop orders, but leaves up to us how to calculate it, to do this triangulation. Yeah? But the fact that we have a definition that can be written on 2 lines is a good starting point to actually try to solve the problem, other than the standard problem of drawing kind of infinite number of Feynman diagrams or do infinite number of cuts to specify the integrand. Now, recently, we made some progress on this. We still cannot calculate the integrand to all loop orders, but we can find some systematics, and instead of single amplitude-hedron geometries, we can kind of break the whole thing into pieces. We call them negative geometries. The details of what these negative geometries are not that important. But instead of one geometry, you have many geometries, and there is a hierarchy between them. So these graphs are so that the vertex in a graph is a loop, and a link is this quadratic inequality. So, and these are complicated. So the simpler graphs have fewer of these links, and more complicated graphs have more links. So more complicated geometries, positive, negative geometries have more links, less complicated have fewer links. And the amplitude, or in particular the logarithm of the amplitude here, corresponds to sum of all of them. So there is some hierarchy of contributions. You can think about it as some sort of expansion using building blocks, but it's not Feynman diagram, it's not the things in the unitarity methods, or it's some geometries, but there is a hierarchy between them. So we can just decide to calculate the simplest ones. And as it turns out, any contributions which don't have internal cycles are simple, like these two. Note that these are not diagrams in the usual sense because the vertex corresponds to a loop. So all of these contributions here are for loop contributions to for loop amplitude. Yeah, this marked point corresponds to the fact that we are not integrating over one of the loops because we care about some object which is IR finite, corresponds to some Wilson loop with the Lagrangian insertions. There are some details, but this is basically a prototype for an IR finite version of the amplitude. We have an expansion using these geometries, and we only can look at the simple ones that we can calculate. And why is it simple? Even for the free loop case, when you have three dots, you can see that the amplitude is a sum of these two contributions, and the one which is simpler has fewer links and doesn't have this internal cycle in this space is a simple function of logs, while this one is a more complicated function of polylogs. So there is some hierarchy even after you integrate. Yeah, so there is a story about the integrand that here we actually integrate because the functions that we are getting here are IR finite, so we can actually integrate if we can or solve some differential equations. So we resummed all the diagrams corresponding, all these contributions to all loops corresponding to these simplest negative geometries. And it turns out in the end we have to solve some differential equation that we found. You can solve it, then you can look at some quantity called gamma cusp, which was something they're very interested in for this object. Gamma cusp plays an important role for capturing the IR divergences in planar n equals 4 super Young-Mills. There is a prediction from integrability what this object is to all loop orders. So we can look at this gamma cusp, we can have something to compare to all loop orders. So this is an exact expression how it looks at strong coupling by resumming all the weak coupling contributions. This is an exact formula, and this was the formula that we gave, that was our approximation, which surprisingly agreed for the qualitative, at the qualitative level. Both of these expressions grew like G at strong coupling. Surprising that we even can get the right order by resumming some ad hoc selection of contributions at weak coupling. And now we are working on the generalization to the more complicated geometries. Okay, I have a few minutes left. So these were the stories about phi cube theory. There is something new with the cosmological correlators related to it. There is also connections to other theories, nonlinear sigma model, Young-Mills theory. There is some connection. Shruti will talk about it a little bit in her talk. And now I will want to say something much more speculative about gravity. There has been always a problem with trying to apply the positive geometry for gravity. I don't know what it is, so this is not announcing any result here. But we made, I would say, incremental progress in this direction. The problem with gravity is at several levels. Gravity is intrinsically non-planar. There is no planar sector of gravity. So we cannot use any of these variables that I was talking about. We cannot use these Xij's. Or we can use them, but they wouldn't make kind of a good sense for that. We cannot use these momentum twisters and so on. We really have to work in a fully non-planar setup. And there are these new types of singularities, these poles at infinity. I was complaining about it at the beginning, that we don't know how to capture in geometry. And in addition, the singularities of the gravity amplitudes are not logarithmic. So we cannot even if we find some geometry, we cannot use these D-log forms that were cornerstone of these positive geometries. So something must be changed at all levels. Changing the geometry, changing the definition of the form. Everything must be new for gravity. Now, we know that there is a connection between the Young-Mills amplitudes, which at least at 3 levels are given by the amplituhedron. Because they are the same in n equals 4 super Young-Mills and in non-supersymmetric theories, and the gravity. So the gravity definitely is somehow must inherit some properties from the Young-Mills. Of course, at loops, we need the full Young-Mills theory, not just the planar limit to capture that. So we would have to also figure out what to do with the non-planar Yang-Mills first. But just looking at the tree-level amplitudes, we know that the explicit expressions for gravity amplitudes are often surprisingly simple. And tree-level gravity amplitudes have some very interesting property. One of them is, despite there are these poles at infinity, once you look at the large Z behavior under the BCFW shift, it's surprisingly good. So there have been a lot of evidence that something good is going on, at least with tree-level gravity amplitudes, but supposedly that will also propagate to loops through the cuts and so on. Now, one very simple expression found like 10 years ago by Andrew Hodges is the closed formula for all MHV amplitudes. So these are the simplest helicity amplitudes. For Yang-Mills, this is given by Park-Taylor formula. So the simplest thing we can imagine. Gravity is slightly more complicated, but there is a very simple compact formula which has some determinant of the matrix in the numerator and it has some simple pole structure in the denominator. Now, if you look at the explicit expressions for 4-point graviton amplitude, 4-point is always artificially simple, but at 5-point, there is a numerator, very simple numerator, and we can we put everything under the common denominator, and we have all poles in the denominator. Now, the numerator is very special. 5-point is given by a trace of P1 slash P2 slash P4, P3 slash P4 slash, but it is actually more interesting than just that. Yeah, it has very magical properties. One property, obviously, it's an amplitude, so it should factorize on a poles. So the numerator should guarantee that whenever you sit on one of these poles, the amplitude factorizes into 4-point and 3-point amplitude. That's always true. Yeah. Now, the question is, can we just look at the numerator, not also at the denominator, not at the whole amplitude, and try to answer, is the numerator fully specified by certain kinematical conditions? And what we proved in the paper, which should show up tomorrow or the day afterwards, is that if we take a property that we have known for a very long time from physics, that there is no pole, that the numerator should vanish whenever we send an angle bracket and square bracket to 0 for a given fixed pair of indices, only imposing that for all pairs fully fixes the numerator. Yeah, there is nothing else that is needed, no factorization, no other information. So the numerator is an answer to certain kinematical question. What is the unique function of angle and square brackets of certain dimension and certain little group weights, which vanishes whenever we set one angle and one square bracket to 0 for all pairs of ij labels? Okay, and just to see how non-trivial it is, if you look at this 5-point numerator that I wrote before, it only manifests 4 out of 10 conditions. So only for 1, 2, 2, 3, 3, 4, and 4, 1 pairs of labels, it makes manifest that it vanishes whenever you send an angle and square to 0. But for these other 6 are non-manifest, and you have to use momentum conservation to rewrite the numerator in a different way, which manifests that. Okay, so the momentum conservation is crucial here. So this is a speculation, the rigidity of the amplitude, the fact that it's fully satisfied. So this is a statement for all n at tree-level MHV amplitude. This, the speculation is that this is basically one part of the replacement of the D-log form to some gravity form. We don't know what is the geometry, but we see that this numerator and these zeros of the numerator should replace the notion of the D-log form in some way to capture the gravity amplitudes. And now I'm over time, so let me skip the summary and go directly here.
The trick of making the last part so interesting that I didn't want to cut you. But we do have time for a few quick questions. Okay.
So you were drawing these positive geometries at some point using these momentum twistors. In order to be able to draw these guys, do you choose like reality conditions for these guys such that they are real? They are purely real?
In order to draw, you mean,
Yeah, at some point you are drawing something with momentum twisters, like
yes, so they are real, yes, yeah.
I see. Okay, so you like do some with rotation, you know?
Yeah,
Yeah,
so they are real. The momentum twisters are always real. Now, the other question is what are the momenta which corresponds to real momentum twisters? And they are not real necessarily. Yeah, so they can be complex. Yeah.
For amplitudes involving massive spinning particles, I wonder what is the progress for the positive geometry.
Yeah, so this is all massless at the moment for the trace phi cube and for the amplitude-hedron for n equals 4. In principle, yes, you can introduce masses. You have to work with other variables, maybe the massive spinor helicity variables. You can work with them. You have to change the definition, so the inequalities would be different. One thing we did recently, which is maybe not directly what you would like to, what you are asking about, but if you go to the Coulomb branch of n equals 4 super Young mills, there are massive particles as well, and for some simple cases, we have a positive geometry for that, for the Coulomb branch amplitudes. So they have masses, but if you would like, for example, massive phi cube or just introduce masses, you just have to work with other variables. But in principle, there is no obstruction. Yeah, but you have to define the definition of the space, and the D-log forms would maybe propagate as well, maybe would change that, we don't know. Yeah, if you have to change the definition of the form as well.
Thanks for the nice review. At some stage, when you do calculations in generic quantum field theories, you have to deal with counterterms. So would counterterms also have a positive geometry interpretation?
Yes. So we don't have this dictionary, but if you just, even before you start with the positive geometry, you just have to, in order to have a hope to have positive geometry, the amplitude must be kind of a rigid object which satisfies certain conditions. So your definition of the amplitude has to involve the counterterms. For example, in nonlinear sigma model, the counterterms are fixed by some soft limit properties. So if this is the case, you have one object has no free parameters, then you can try to translate it to some positive geometry, find this map between kinematics and the geometry. But in order to be able to do it even, you cannot just have a theory with free parameters. Yeah, you have to fix these parameters. You have to have a rigid theory. So if you do, yeah, there is a hope. Of course, as I said, there is no dictionary at the moment, but at least you can start to work on it.
All right, so let's stop here and thank Jaroslav again.